Okay, chapter 18, we finally get into the world of inference, where we are doing decision making based on samples. And the first decision making procedure we learn is called a confidence interval. Now, you don't have to write that down yet, we'll get that a little bit later, but the goal is to use a sample to make a prediction about what's in the population that we don't get to look at. So, we have, let's just go straight to an example. We have this local paper that polls a random sample of 320 voters. That sounds like a sample size, right? That's going to be an N, pretty sure. 144 say that they will vote yes on the school budget. Okay, yeses and nos put us firmly in categorical world, which is actually where we're going to stay until the end of this unit. Everything we do from here till the next test is going to be proportions. It's going to be categorical data. So we don't have to worry about Y bars. We don't have to worry about sigmas. They're not going to be there for a while. So this is 144 yeses out of 320. So that's a part of the whole, which means there's probably going to be some proportions floating around here pretty soon. So yes voted yes on the school budget. We'd like to use the sample to predict P, which is the proportion. I don't know why the word B is there. Mark that out. I don't think that's supposed to be there. B is not supposed to be there. All right, we'd like to use the sample to predict P, the proportion of all voters that vote yes. So let's review notation. P with no hat is a population parameter. It is the percentage of successes for the entire population. We don't know that. We have no idea what the population parameters are. So let's get to this question. What information do we have, do we not have? Well, we don't know what all voters are going to do. We know what 320 voters think. But we don't know what all the voters are going to think or what they're going to even do when it comes up for the vote at Election Day. So we have a sample proportion. I'll jot some things down here. P hat. Well, now let's see. We actually need to compute it. So a P hat is how much out of the whole. So 144 out of the 320, which we could leave as a fraction. I know y'all are fractionally challenged and you don't really like them much. So let's just go ahead and change that to a decimal. So we'll divide 144 by 320 and we're going to get some magic number like 0.45. So about 45% of this group of 320 people said that they were going to vote yes on the school budget. Which means right now, if we can count on this sample to be representative of the population, it's looking like maybe the school budget is not going to pass, because you'd have to have a majority vote for that to pass, and 45 is not a majority. So we've learned something about a sample from the population. We know that, but we still don't really know what the population is going to do. So when Election Day comes around and people actually vote on the school budget or not, then we might get something different than 45%. We might get 52% who say yes. We might get 40% who say yes. So this is just one sample statistic that gives us insight into what we think might happen at the next election, but it may be wrong. That may not be what actually happens. So we have a sample proportion. We do not, let's jot some things down here, we do not know the population P, the true proportion of people who are going to vote yes on the school budget. But good samples often give us a picture of the population. So it's looking like if we really want this school budget to pass, we're probably going to get out and do some campaigning, do something to try to get people on board. Let's say that I want to maybe use a normal model to answer some great question about the percentage of people who are going to vote yes on this new school budget. So let's get back to assumptions, conditions. If we want to use a normal model to answer some great question, what conditions will we have to meet if we're in P hat world? So there's 3 conditions for P hat world. The first one is we have to have a random sample. Did we have a random sample? Yep, there it is. Magic word, random. So let's jot some things down. A random sample of voters was used. Check. Okay. So first condition's met. Okay, second condition is that either all of our people that we sampled have to have independent ideas about whether they're going to vote for a school budget or not. Or I could even go with the 10% condition. Is 320 people less than 10% of all voters? So in a place that has a school district that's going to vote on a school budget, would there be more than 3,000 people there? Chances are probably so. So I think I'm gonna put a weasel word in here. 320 voters is probably, there's my weasel word because I'm not sure, probably less than 10% of all voters in any typical place with a school district, with a school system. Now, if for some reason that turns out not to be true, then everything I do from here on out, it's kind of off kilter. It's not really all that dependable. So I need that to be true. All right, last but not least, I need to check my successes and failures. So that means I normally look at my N times P and my N times Q. Okay, so N is 320. P is unknown. Darn, now what am I going to do? I don't know P, because P is the true proportion of voters who are going to vote for the school budget. I don't know that. What do I do? Okay, well, what do I know? I know P hat. P hat's supposed to be, if I have a representative sample, pretty darn close to what the truth is. So I'm going to use, in the absence of P, I'm going to use a P hat. And my P hat is 0.45, or you know what would be easier? It'd be easier to do 144 over 320, and the 320s would cancel, and you just get a 144. Didn't we already know that 144 people voted yes? Those are the number of, instead of expected successes, those are the number of actual successes. But it's definitely more than 10. So chances are, in the big scheme of everybody, we're probably still over 10. All right, going to do the same thing for my hats. So N times Q hat is 320. If 55% say yes, 45% say yes, then the other 55% probably said no. And that's the other, let's see, 320 minus 144 is 176. So I have 144 yeses. I have 176 no's. Those are both at least 10. Both at least 10. Check. Alright, so if I wanted to answer some fabulous question about the percentage of people who are going to say yes on the school budget, and I need a normal model to answer that question, then I've met the conditions to use the normal model. So I'm going to just, after I write all that down, I'm going to say a normal model can be used. I'm going to try to make that a habit in the future, because from here on out I'm actually going to write up very structured procedures, and part of the procedure is checking conditions and giving the conclusion to what it means when those conditions check. And when these are all true, that's how we know a normal model can be used. We're going to make that a blanket statement. We say after the conditions check. If they don't check, then you'd have to write something different, like, well, normal model might be appropriate, but we can't be sure because this condition didn't check. So we want to say what's true, and we're banking on this assumption on the second one being true. Okay, so we could use a normal model if we needed to. Good to know, because I'm probably going to throw a model at you sometime real soon, because it kind of rules the statistical world most of the time. Alright, what next? If I'm going to use a normal model, I'm going to need some parameters. And parameters are like a mean, let's see, or like a true proportion, which I don't actually know, and a standard deviation of p hats. Oh, okay. Now that I could probably get. But we know p hat and we don't know p. So calculating the standard deviation is a little bit of, there's a little bit of a technicality here, because technically the standard deviation of all p hats in a sampling distribution is the square root of p times q over n. That's a standard deviation formula we've used before. The catch is we don't know p and q. So what did we do on the last page when we didn't know p and q? We used the hats instead as an estimate. Okay, so the best we can do, since we don't know what's actually in the population, is to use an estimate. So if we use an estimate, that means we've got to do the square root of p hat times q hat over n. So we just use the hats instead of the p's and q's that we don't actually know. Which means this might have more error in it than what we would have gotten with the true proportion. Which means we need to change the name. So this is no longer standard deviation. This is now called the standard error, and you can't use a sigma anymore because sigma is for a standard deviation. So what do statisticians decide to do? They're just going to abbreviate SE of the p hats. So this is read standard error of p hat. It's the same formula as standard deviation. You're just going to use the hats instead. Okay, let's put some numbers in. Let's look at this. Let's see what the standard error for our yes voters is. So square root of, we had 45% who said yes. We had 55% who said no out of 320 people that were surveyed. And I'm going to assume you can put that in the calculator all by yourself and come up with 0.0278 without my help. So we're just going to go ahead and skip to the answer. So I have a way to measure spread. I know that my pictures of all my p hats should be approximately normal because my conditions checked. Okay, let's see what else we got to do. We're going to make a prediction about the population. So we've already kind of made a prediction. We took a sample, and in the sample 45% of the people said yes. So I could say, okay, so I think 45% of the population is going to say yes. But I don't really believe that because my sample could be wrong. So maybe I want a little wiggle room. I want to have an interval, maybe. More or less than 45%. So we're going to need one more thing. How sure do we want to be that our prediction about what the population is going to do is right? Do we want to be 90% confident? Do we want to be 95% confident? Do we want to be 98% confident? Do we want to be 99% confident? You're never going to be 100% confident unless you say it's between 0 and 100%. Then you could be 100% confident. But that's kind of a dumb answer because we already knew that. That's true all the time. And if you go lower than 90, that's not a lot of confidence. If you don't have enough confidence, then what's the point? So we want to make a good estimate about what's in the population. And we want to be able to quantify how good that estimate is. So that's why we need to choose how confident we want to be. All of these are sort of readily acceptable good choices for level of confidences, 95 being the most popular. Because, 95 is one of those nice numbers that takes us 2 standard deviations from the mean in both directions. Okay, so what I'd like to do is, after I pick a level of confidence, so I pick a level. Let's say I'm going to pick 95% because it's just my favorite. I need to find a z-score that corresponds to it, and we call that z star. Okay, so let's make some notes here. Let's use 95% confident this time. I'm just going to pick one. Some other time we'll use 98 and 90 and some other fun stuff. So if I find z-scores that border the middle 95% of a normal curve, what's that going to look like? All right, let's look at a picture. All right, so here's a picture of the percentage of yeses in the population. And there's some true p that I don't actually know. I have a p-hat to estimate it. My p-hat was 45%. So it might be 45%, but that might be wrong. Because it's just based on a sample, and sampling has variability in it, and so one sample might underestimate, one sample might overestimate. I don't know what mine's doing. But I do know that if I want to be 95% confident that I'm predicting pretty close to what's in the population, I got to go out 2 standard deviations from the mean, approximately. Because I know that between negative 2 standard deviation below the mean and positive 2 standard deviations below the mean lies 95% of all possible samples. My sample, I'm 95% sure that my sample is within 2 standard deviations of the truth. That's kind of what I'm getting at. That's pretty confident, by the way. Alright, so this is, well, okay, this 95% here, that's actually an estimate of what's between a z-score of -2 and a z-score of +2. That's not really quite right. It's close. What really should it be? Oh, I need a calculator, right?